Hello my dear students, welcome back to the class. In our previous class we have learnt about the force between the two parallel conductors carrying the current. Force between the two parallel conductors which is carrying the current. And we have also learnt about the definition of the current or 1 ampere. Correct? So in today's class we are going to learn about the expression for the torque acting on a rectangular coil or a loop which is carrying the current in a magnetic field. So we will write down torque acting on a expression for torque acting on a rectangular current carrying loop placed in a uniform magnetic field. Okay. So what we have to do is, let us consider a rectangular coil. Okay, I will consider a rectangular coil. Let me mark it as A, B, C, D, which is carrying the current I. Okay, it carries the current I. Fine. And it is placed in a magnetic field, uniform magnetic field. Okay, it is placed in a uniform magnetic field, B. It is placed in a uniform magnetic field, B. Let A be the length and B be the breadth of the coil. Let A be the length and B be the breadth of the coil. M be the normal drawn to this surface or plane which is carrying the rectangular coil. So the normal drawn is outside. So therefore the normal drawn to this surface is this one. Let me mark it as M. Normal drawn to the surface, M vector. Theta be the angle between the normal and the magnetic field. Okay, theta be the angle between the normal and the magnetic field. Now, the next what we have to do is, see here, using the Fleming's right hand rule, we can say which is the direction of the force. See, this is the direction of the current, this is the direction of the magnetic field, correct? Then the force is this way. This is the, so the force acting on the length A and arm, or else I can say the force acting on the arm BC and AD are equal and opposite in direction. So what happens? That force will get cancel out. The force on the arm BC and AD will be equal and opposite in direction. Therefore, they can say they act along the axis with the equal and opposite direction. So therefore, it will get cancel out. The next, what about the force? See here, the current is in this direction, magnetic field is in this direction. Therefore, the force acting on this. So I can say, see here, current, current and magnetic field, then the force will be, correct? Using the Fleming's right hand rule, we can say once force here, if it acts here, then the force acting at this point will be opposite, equal and opposite. Even in the on the arm BA or AB and CD also, the force acting is opposite, but there exists a torque or couple acts. See, for example, I have this over here. It's a rectangular in shape. I will say A, B, C, D. Okay, force acting on this one will be equal and opposite, so they'll get cancelled out. Here the force one is pulling in this side, the another force is pulling in this side. Force gets cancelled out, but it starts twisting. Couple force acts. That's nothing but torque. Torque will start acting on this body. So therefore I can say the force on the arm AB and CD are equal and opposite, but there exists a torque. What that force is, let me draw it as F1 and F2. Okay, so I will mark F1 and F2, that is equal to Bill sine theta, correct? F is equal to, or F1 is equal to, F2 is equal to B, magnetic field, I is the current, correct? Length is B, Bill sine theta, sine theta. What about theta? Theta is the angle between I and B. The angle between I is this one, B is this one, the angle between them is 90 degree. So therefore theta is equal to, since theta is equal to 90 degree, I can say F1 is equal to, F2 is equal to BIB. They are equal and opposite, and I can say it is equal to BIB. Why theta is equal to 90? Because angle between the current and the magnetic field is 90 degree. So therefore I can say theta is equal to 90 degree, and hence F1 is equal to, F2 is equal to BIB. They are not collinear. This results in a couple. They are not collinear like what we have here. It will start pulling. So therefore, since they are not collinear, not in the straight line, collinear means, since they are not collinear, there exists a couple, correct? This results in a couple. This results in couple. Okay, that is nothing but torque. Torque is nothing but force into perpendicular distance. Torque is equal to force into perpendicular distance. How to find this force into perpendicular distance? See here, force is this one, correct? BIB. Force is BIB. Okay, perpendicular distance. How to calculate the perpendicular distance? What is that perpendicular distance? Perpendicular distance is this one. What is this distance? We don't know. Okay, so we have to measure this perpendicular distance. Now look here, I will redraw this over here so that you will understand, or somewhere here I will draw it so that you will understand. See here, this is the diagram. From the top view, if you look here like this, okay, this is a magnetic field, and if this is the normal drawn to the surface, anywhere I can draw normal to this surface, I have drawn it here. The angle between the normal is and the magnetic field is theta, and then I can say this angle between the normal and this one is theta, and the line joining this one, that is this total, it is like this, correct? Our rectangular coil. So therefore this full is 90 degree. That is nothing but, I'll put it as alpha. See, this rectangular coil ends here like this, correct? So therefore, see here, this is alpha, this is 90 degree, and then what is this angle? Total it should be 180, so this will be theta. If this is theta, then this will be theta, correct? Now, sine theta is equal to, from the diagram, what we can say? Sine theta is equal to opposite by hypotenuse. Opposite is, let me write it as A, B, C over here, or we'll write PQR. PQR, okay? Or sine theta is equal to opposite by hypotenuse PR by PQ. Then I can write PR is equal to, that is our perpendicular distance, is equal to PQ into sine theta. What is this distance? A. Correct? So A sine theta. Understood how it is? Can see the board, no? Okay. See here what we have done. We have redrawn it, or we will just look it carefully. Okay. This is the normal drawn to this surface. Okay. This normal drawn to the surface. So this normal drawn to the surface should be perpendicular to the plane. Correct, no? Normal means like this. The normal drawn to the surface is perpendicular to the plane. So the angle between them and the plane is 90 degree. See here, this is the normal drawn to the surface. Okay, exactly perpendicular. Now where is our theta? Theta is, where is our theta? Theta is somewhere here. So this angle is fully, it is 90 degree. Plane and this one. This, see here. I'll bring this one over here. This is actually fully 90 degree. That here, theta plus alpha is equal to 90 degree. So therefore I can say if this is alpha, this should be theta. Then, therefore I can say what? Why if this is alpha, this should be theta? This full is 90, correct? 90 minus alpha is theta. So this is alpha. 90 plus this should be theta to become 180 degree, because in a triangle it is 180 degree. Okay, alpha, theta and 90. We want this distance, perpendicular distance, that is this one. From here to here, this distance we want, that is our PR. To calculate this distance, I can write sine theta is equal to opposite by hypotenuse, that is PQ. PR by PQ. Sin theta is equal to PR by PQ. We want to calculate PR. Therefore, sin theta into PQ is equal to PR. PQ I can write it as A sin theta. So therefore, I'll write here perpendicular distance as A sin theta is equal to tau. Tau is equal to A sin theta. Okay. Now look here. A is nothing but length into breadth is B. Length into breadth is area of the rectangle. So therefore I can write tau is equal to B I area into sine theta, where A is equal to B into A, or A into B. Next step. What I can write? See here, I into A is nothing but magnetic moment. So therefore, I can write magnetic moment. Shall I erase the heading? Okay, thank you. I can write magnetic moment. Since M is equal to I into A, we can write tau is equal to B M sin theta. Correct? One A is, IA. Okay, B M sin theta. Or else we can write tau is equal to M cross B. Tau vector is equal to M vector cross B vector. In terms of vector form, we can write tau vector is equal to M vector dot B vector. Why? Because M vector is equal to magnetic moment. M vector is equal to I into A vector, where A vector is a area. Correct? How? So understood how it is? What we have done? We have considered a rectangular coil A, B, C, D having the length A, breadth B, carrying the current I. Okay? Which is carrying the current I. Theta be the normal drawn to the surface, and B be the uniform magnetic field acting on the rectangular coil. We can say the force acting So I will write over here, that is in the beginning you should write, that is force. Forces on arm BC and AD are equal and opposite. Equal and opposite. They are equal and opposite and act along the axis. Act along the axis. Hence, they will get cancel each other. Hence, they will get cancel. Next, force on the arm AB and CD. Force on the arm AB and CD is F1 is also equal and opposite, or are equal and opposite. That is F1 is equal to F2 is equal to BIB sin theta, or F1 is equal to F2 is equal to BIB. Why theta is equal to 0? Theta is equal to 0 because it is the angle between the normal drawn to current and the magnetic field. The angle between the current and magnetic field is 90 degree. So therefore I can write theta is equal to 90 degree. F1 is equal to F2 is equal to BIB. Since they are not collinear, even though forces get cancelled, there results a couple, that is torque. Tau is equal to, we know that tau is equal to force into perpendicular distance. To calculate perpendicular distance, I have redrawn it. How? This is the from the top view I have drawn. See here, this is a normal drawn to the surface that I have drawn it over here for this point, that is here. If I draw the normal to this surface, then theta is the angle between the horizontal, that is perpendicular distance, and then this is our the rectangular coil which we have placed. If this is theta, then let it be alpha. Actually this should be fully 90 degree. So if this is 90, then this should be theta. Then from this we can write sin theta is equal to opposite by hypotenuse, PR by PQ. We want PR, so PR is equal to PQ sin theta. PQ is A, so therefore we can write A sin theta is equal to PR. So we have written here A sin theta for perpendicular distance, but B into A is nothing but area, so I can write BIA sin theta. But I into A is nothing but moment, therefore I can write magnetic moment as I into A vector is equal to M. So I can write tau is equal to Bn sin theta, or we can write in the form of a vector, that is tau vector is equal to M cross B vector. This is the expression for the torque acting on the rectangular coil which is carrying the current placed in the uniform magnetic field. Okay. When this magnetic moment, even though if it is, this magnetic moment may act normal, this magnetic moment, either it might be parallel or anti-parallel to the magnetic field, then write one note for your reference purpose. Okay, shall I erase this? When M vector is parallel or anti-parallel to magnetic field, parallel or anti-parallel to magnetic field, anti-parallel to magnetic field, tau becomes 0. Parallel or anti-parallel means theta is equal to 0. When theta is equal to 0, sin 0, 0, therefore tau is equal to 0. Understood? When M is that parallel or anti-parallel means theta will be equal to 0. So therefore we can say tau is equal to 0. This indicates the state of equilibrium and there is no torque on the coil. It is so if M vector is parallel or anti-parallel to B, tau is equal to 0. That is nothing but it is in the, we can say it is in equilibrium. Okay. If loop has n closely wound turns, that is instead of one rectangular coil what we have taken, if we have n number of coils in that, then we can write M is nothing but equal to n into I into A. For solving the problems we need this. Okay, M is equal to n into I into A. So this derivation what we have done, it is for the torque acting which is on a current carrying loop, a rectangular loop placed in the magnetic field. Next what we are going to do is, we are going to learn the expression for torque itself, but we will place this plane parallel to the magnetic field. Okay, we will place parallel to the magnetic field. So I'll write torque expression for torque acting on a rectangular current carrying loop. Okay, current carrying loop placed with its plane parallel to the magnetic field. Plane we are keeping that it's a plane parallel to the magnetic field. Okay, so let me consider a rectangular coil. Now we are placing it parallel to the magnetic field. Okay, this is now plane is parallel to the magnetic field, correct? That time we did not place it in parallel. Okay, let us consider a coil, rectangular coil A, B, C, D with the length A and breadth B. Okay, let B be the magnetic field acting on the plane, acting parallel to the plane. Okay, M be the normal drawn to the surface. Correct? M be the normal drawn to the surface. So from this magnetic field exerts no force on the arm BC and AD because they are equal and opposite. Therefore, total force is 0. The force on AB and CD, they are also equal and opposite, but there acts the torque, that is nothing but couple. So therefore what I can say is, just like previous one, force acting on the arm AB and CD, F1 is equal to F2 is equal to BIB sin theta. What about theta? Theta is the IB the current. Okay, so I forgot to mention the current. I be the current. Theta be the angle. Theta is nothing but angle between the magnetic field and the current, that is nothing but 90 degree. So therefore what we want to say here is theta is equal to 90 degree. Hence we can write F1 vector, F1 is equal to F2 is equal to BIB. Since they are not collinear, there acts a couple, same concept we can say over here, correct? So what I can say here is F1 is equal to F2, they are same. See, both they are acted out of the paper like this. force is acting out of the paper using the Fleming's left hand rule. Okay, Fleming's left hand rule. We have to use Fleming's left hand rule. The force, Fleming's left hand rule, like this. So it is acting out of the paper. Here it acts like this, out of the paper. So F1 is equal to F2 is equal to BIB. In that time also I just mentioned, I think A has a right hand. It is not right hand, it should be left hand. Okay, so that when you draw you will get a clear picture. See, this is a Fleming's left hand rule, using Fleming's left hand rule. So it is equal and opposite in magnitude and also in direction. This net force in the loop is 0, but there is a torque on the loop due to the pair of forces F1 and F2. Okay, the forces, they are equal and opposite in magnitude and direction. They cancel out, but there exists a torque. So torque is nothing but force into perpendicular distance. So therefore what I can write, force, now which is the perpendicular distance from here to here. However, it is parallel, so therefore I can write directly as F into A. But what is F? F is equal to, F1 is equal to F2 is equal to F, that is equal to BIB into A. B into A is nothing but area, so therefore I can write BIA is equal to tau. BIA is equal to tau. Then we know that M is equal to I into A, therefore I can write tau is equal to B into M. This is the expression for the torque acting on a rectangular current carrying loop placed with its plane parallel to the magnetic field. Understood? So if it is placed parallel to the magnetic field, then tau is equal to B into M. If it is not placed parallel to the magnetic field, then tau is equal to MB sin theta, or B tau vector is equal to M vector cross B vector. Understood? So there is a small changes for parallel and without parallel. If it is parallel, that is just BM or MB, whereas if it is not a parallel, then it is MB sin theta. Okay, shall I move further? Yes. The next concept which we are moving for is we have to show that current carrying loop behaves as a magnetic dipole moment. Current carrying loop behaves as a magnetic dipole moment. That is M vector is equal to I into A vector. Okay, it behaves as a magnetic dipole moment. We have to show how we can do. Let us consider a circular coil. Okay, we have used for Biot-Savart's law, correct? Using that we have derived. Do you remember? Okay, so let us consider a current carrying loop of radius R, carrying the current I. Let I be the current through the coil. Okay. Magnetic field along the axis at a distance x. At a distance x we will be speaking. Magnetic field B is equal to, what expression we got for that using Biot-Savart's law? B is equal to mu naught by 2 I R square x square plus r square to the power 3 by 2. This was the expression which we found using that Biot-Savart's law. Correct? Here, if x is greater than r, then what we can write? B is equal to mu naught by 2 I r square by x to the power 3, because x square into 3 by 2 will become x cube. So therefore B is equal to mu naught by 2 I r square by x cube. See, we know that area is equal to pi r square, correct? R square is there, radius is here, but we don't have pi. So multiply and divide this equation. Multiply and divide 1 by pi. So we get P is equal to mu naught by 2 pi I pi r square by x cube. So we can write mu naught by 2 pi I a divided by x cube. I into a is nothing but m. So B is equal to mu naught by 2 pi m by r cube. Or else we can also write it as, if you multiply and divide by 2, I can write this expression as B is equal to mu naught by 4 pi 2m by r cube. So this is the expression for the magnetic field, or expression for the magnetic field, which is we can say that current carrying loop behaves as a magnetic dipole moment. See here, it behaves as a magnetic dipole moment. So therefore this is due to the, that is this expression is similar to what? Is this expression similar to the electric field due to the dipole? This expression, is it similar to the electric field due to a dipole? What was the expression in that chapter we got? Expression for the electric field due to a dipole. Do you remember? We got one expression as E vector is equal to 1 by 4 pi epsilon naught. What was the expression we got? 2p vector by x cube. 2p vector by x cube. Similarity, see here, this is 2m, here it is 2p. There we have written in terms of p, here we are writing, that is dipole moment, then here we are writing it as magnetic moment, correct? So therefore we can write the electric dipole moment. Here it was electric dipole moment, this is magnetic dipole moment. Understood? This is electric dipole moment, this is magnetic dipole moment. So the expression of this B is a magnetic field and electric field. They are same. This is expression for magnetic field due to a dipole. This is expression for magnetic field due to a dipole. Magnetic dipole moment. Correct? So similarly, like this only, if we derive for at an equatorial line, then we get the expression as B is equal to, this is for the current carrying loop behaves as a magnetic dipole moment, correct? Similarly, at an equatorial line, if we derive, we get B is equal to mu naught. Where shall I write? Shall I erase this? Okay, we can write it as B is equal to mu naught by 4 pi m by r cube. We get for a magnetic m by x cube. I missed here, I'm sorry. Thank you. You're right, x cube here. Okay, so we get here into x cube for an equatorial line. If we derive like this, okay, no derivation, at equatorial line, we get the expression B is equal to mu naught by 4 pi m by x cube. See, in vector form, if we write B vector is equal to mu naught by 4 pi 2m vector by x cube. So similarly, in case of the electric field on a bisector of the dipole, we get E vector is equal to mu naught, 1 by 4 pi epsilon naught P vector by x cube. This expression we get for a electric field. That is, the expression is nothing but electric field on a bisector of the dipole. So these are the similarities between electric field and magnetic field. What is the SI unit of the magnetic dipole moment? See here, that is m is equal to I into A. So area into meter square is the SI unit of ampere meter square. I is the ampere, area into area means meter square. So I is ampere meter square is the SI unit of the magnetic dipole moment. Understood? Shall I move further? Next we have one small derivation, that is which is very very important for 5 marks. Okay, let us see it in the next class. Thank you.